Dr. Rodolfo Leyva, who's a lecturer in quantitative methods in the School of Social Policy at the University of Birmingham. His research examines how social, psychological, political, and cultural factors shape public attitudes, decision-making, and behaviour, with a particular focus on mass media, inequality, and intergroup relationships. Methodologically, his work combines survey research, experiments, quantitative modelling, and interdisciplinary behavioural science approaches. His current research is investigating and testing the determinants of public support for structural climate change policies. So, really looking forward to hear what you've got to say today, Rudy. Thanks.
I think anyone's ever said that before. So, hi, folks. My name is Rodolfo Leyva. Rudy, which most people find easier to pronounce. Thank you very much for inviting me. And so, the title of my talk, I guess, asks the question that sounds simple enough, but no, isn't. What are we modeling when we model human behavior? So consider a simple example like medication adherence. You include a variable called motivation, but where did that variable come from? What does it actually capture? And what are you assuming about the human being behind it when you plug it into your equations? This isn't an abstract puzzle. It's in interdisciplinary modeling, whether for epidemics, energy transitions, or public policy. Behavior enters formal systems as tidy variables such as compliance, adoption, trust, etc. Yet behavioral science tells us that these are not simple levers, right? And action is embedded in psychological states, social norms, and institutional infrastructures. We are not just interested in what people do, but in the processes that makes their behavior intelligible. So the real question is not how to model behavior. It is what kind of object are we claiming to model? That is what I want to unpack today. And so this question matters because behavioral variable is rarely primitive. By the time something appears in a model as, let's say, support, risk perception, compliance, or adoption, it has already passed through a series of conceptual and methodological decisions. We have selected a phenomenon, interpreted through theory, defined constructs, operationalized these constructs, collected data through various means, and then specified a model, and then drawn an inferential claim. If we fail to keep these steps separate, we risk treating a survey response as an attitude, an observed act as a motive, or a latent variable as a real psychological entity, or a regression coefficient as a mechanism. These are not merely philosophical mistakes. They are all too common methodological misinterpretations that affect interventions, policies, predictions, and what we think we have learned. So behavior modeling is best understood as representation under conceptual and measurement uncertainty. The formal model may be precise, but the mapping between the model and the human phenomenon may be uncertain. That's not a weakness that's unique to behavioral science. It is a modeling problem. But in behavioral science, it is especially consequential because the objects of interest are often interpretive, contextual, reflexive, and only partially observable. And a first clarification that I'd like to make is that behavior is not just one kind of object. Human behavior can often be directly observed. Anthropologists, for example, observe social practices. Psychologists observe choices in experiments. Sociologists observe interactions in institutions. Economists observe transactions, and political science observe voting patterns. However, behavior science works across a spectrum. At one end, there are actions, what people do. Then there are choices, sanctions among available alternatives. Selections among available alternatives. Then there are self-reports, what people say they do, think, feel, believe, or intend. Then there are interactions, right? Behavior in relation to others. Then there are contexts, institutions, norms, incentives, infrastructures, cultural meanings. And finally, there are theoretical constructs, often unobservable cognitive phenomena, such as attitudes, beliefs, motivations, values, etc. Again, some of these are directly observable. Some are measured indirectly, and some are theoretical constructs represented through formal models. This is why precision matters. A behavior, a self-report, A construct, a variable, a latent factor, and a causal mechanism are not the same thing. From a formal perspective, moving along the spectrum also changes the ontological status of the variable, and thus the permissible mathematical operations. Observable facts give us event counts or binary outcomes. Self-reports give us often, ordinal Likert scales, which are not interval data unless we impose very kind of strong assumptions. Constructs like trust are modeled as latent continuous variables, but they are estimated from discrete indicators. So if we treat an ordinal Likert item, for example, as an interval continuous variable, we are making a modeling assumption, not a mathematical fact. And the challenge for formal modelers is that the mathematical structure of the variable is itself part of the inferential decision, not a property of a real-world object. And so the organizing framework for this lecture, just for simplistic purpose, I'm just going to refer to it as the behavioral science inferential cycle. Behavioral science often begins with a phenomenon, anomaly, or practical problem. Something appears pattern, puzzling, consequential, or theoretically interesting. The first step is to turn that phenomenon into a viable research question. Right? What exactly are we trying to describe, explain, or predict, clarify, or intervene on? The next step is conjecture hypothesis. What relationship, mechanism, process, or boundary condition do we think may be operating? The hypothesis then requires constructs. For example, if I hypothesize that perceived fairness increases policy support, I need to specify what I mean by perceived fairness and what I mean by policy support. Those constructs then have operationalized through measurement. Measurement generates data under a particular design. Those data are then represented through statistical or mathematical modeling, and from that modeling, we make an inferential claim. Finally, the claim feeds back into theory. It may support, refine, restrict, or challenge that theoretical account. The point is not that research always follows this exact sequence, and it doesn't. In practice, behavioral science is iterative. Sometimes theory comes first, sometimes the anomaly comes first, and other times, like measurement, reveals patterns that we did not anticipate. So cycle here is just a informal model, if you will, that identifies the main transition where behavioral science can become imprecise. And each transition in the cycle is lossy, right? There's information that gets lost, and necessarily so in each step. The phenomenon is simplified into a research question. The research question is then narrowed into a hypothesis. The hypothesis is expressed through constructs. Constructs are approximated by measures. Measures generate data under a specific design, and models impose assumptions on those data. And that inferential claim is conditional on the validity of the preceding steps. Of course, this does not mean that behavioral science is unscientific. It just makes a science in which the inferential architecture must be explicit. Abstraction is necessary. Without abstraction, there is no model. So the danger is not the abstraction itself, but rather forgetting what has been abstracted away. So throughout the talk, I want to emphasize a simple principle, that a model can be formally precise and still be substantively ambiguous if the earlier inferential steps are unclear. And so one of the most pressing distinctions is between constructs, measures, variables, models, and estimates. Construct is a theoretical concept, right? Trust in government, perceived fairness, ideology, identity, motivation, anxiety. These are all constructs. A measure is to generate a variable in a construct. A variable is the formal representation of that measure in a data set. A model is the formal representation of the selected relationship among those variables under assumptions. And the estimate is the model-dependent quantity. It is not the phenomenon itself. So let's take trust in government as an example. The construct is trust. The measure might be a survey item asking respondents how much they trust the national government, maybe on a scale from 1 to 10. The variable is the numerical coding of that response. A Leyva factor might be a statistical representation inferred from several items. A regression coefficient involving that factor is the estimate within that model. Now, that's all cool and elegant, but at no point in that process have we literally observed trust as a substance in the world. Again, that doesn't make the construct useless, but it does mean that the evidential claim depends on how well that construct has been defined, measured, and how well the model represents the hypothesized process. This distinction will be obvious to anyone familiar with measurement models, but it is surprisingly easy to lose in applied behavioral research. Unfortunately, it often is. So the latent variable is not literally the construct. It's just a formal representation within a measurement model, and the model itself is not theory. And there's another related layer that behavioral scientists sometimes underplay. The people that study are themselves inferential agents. They interpret situations, attribute motives, they infer norms, anticipate consequences, justify actions. They also make sense of what they are being asked, what they are being shown, and what they think others expect from them. They also don't do what they're told, and they often lie, which is very complicated in accounting for that in our particular research. And so inference is not simply one thought following another. It involves taking something to be a reason for something else. That matters because our model of a participant's behavior may not match the participant's own reasoning. Suppose, let's say, we use a fairness communication frame, right? And we find that it increases support for a climate policy. We might interpret that as evidence that fairness considerations increase policy endorsement. But what happened psychologically? Right? Perhaps the participant reasoned that the policy was just. Perhaps the frame triggered a moral effect, or it cued identity consistency, or it signaled ideological compatibility. Maybe it increased social desirability, or perhaps it just simply made the policy sound better. The behavioral outcome may be the same, but the process may differ. So behavioral modeling often involves two layers of inference: the participant's inference about the situation and the researcher's inference about the participant. For modelers, this introduces a kind of fascinating formal complexity. If we model the participant as a passive, almost mindless respondent to stimuli, we are effectively assuming a stimulus response data generating process. But if participants are active inferential agents, they are engaging in something closer to like a Bayesian belief updating process. They have subjective points, priors about the experiment, the context, the experimenter's expectations, and social desirability, as well as, and their response is a posterior condition on that interpretation. This also invites kind of strategic or game theoretic perspectives. Participants may not merely reveal preferences. They may strategically adjust their responses based on what they think the policy consequences are. So treating them as kind of passive sources of data ignores the fact that their outputs are already the product of an internal inference. Behavioral science also requires levels of analysis. The same sort of action may have biological, psychological, interpersonal, institutional, and cultural explanations. None is automatically the correct level. Consider, for example, a missed medical appointment. It might reflect forgetfulness, anxiety, depression, distrust, transport issues, work precarity, childcare responsibilities, administrative complexity, or discrimination. A model that treats non-attendance as low motivation may be formally elegant, but substantively wrong if the behavior is constrained by infrastructure. The same applies to climate behavior. People may support low carbon transportation, but lack affordable alternatives. They may value energy efficiency, but live in rented housing. They may endorse climate action, but distrust how costs are distributed. Multi-level thinking protects us against two opposite errors: individualizing structural constraints and structuralizing individual differences without evidence. The key point here is that no single scale is privileged in advance. The relevant level depends on the phenomenon, the research question, and the claim that we want to make. For quantitative modelers, this is not just a conceptual advice. It directly affects model specification. When we ignore this, we commit to classic fallacies. First, the ecological fallacy, assuming that group level correlation tells us something about individuals within that group. For example, if richer neighborhoods have higher vaccination rates, we cannot infer that rich individuals are more likely to vaccinate. It might be the infrastructure, not individual wealth. Conversely, the atomistic fallacy, which is kind of the reverse ecological fallacy, assumes that individual level effects aggregate linearly to the group level, ignoring emergent properties like social norms or peer effects. In multi-level models, this means we must be precise about whether our random intercepts or slopes and our cross-level interactions are capturing individual psychology, group dynamics, or institutional constraints, and whether we have the data structure to separate them. Furthermore, like prediction, explanation, causation, and mechanisms are also different claims. A model may predict behavior well without explaining it correctly. A causal model may identify a meaningful effect while having only modest predictive accuracy. A mechanism claim requires more than evidence of an association, and even more than evidence of a total causal effect. Prediction asks, can we forecast Y? Explanation asks, why does Y occur? Causation asks, what would Y be under an intervention or mechanism asks, do what processes X affect Y? The counterfactual logical causal inference is useful here. To say that X caused Y is to ask what Y would have been under different conditions of X. In experiments, randomization largely helps to approximate that comparison. But experiments are expensive, time-consuming, and so in behavioral research, we often have to rely on self-reported questionnaires. And in this observational research, we require stronger assumptions about confounding, selection, measurement, and model specification. For behavioral science, the danger is that psychological language can make associations sound causal. Saying that trust predicts compliance is not the same as showing that increasing trust would increase compliance. Nor is it the same as specifying the mechanism through which trust operates. The same coefficient can thus support different claims only under different assumptions. Parenthetically, I found it a useful way to formalize the distinctions on the previous slide by using Pearl's ladder of causation, which might likely be familiar to many of you. At the first level is association. This is the level of prediction. It asks, if I observe X, what can I infer about Y? Much behavioral modeling operates at this level. For example, if someone reports low trust in government, can we predict lower compliance with public guidance? That may be useful, but it remains an associational claim. The second level of intervention, this is where causal explanation and total causal effects enter. Here, the question is no longer simply, what does X tell us about Y? But what would happen to Y if we intervene on X? For example, if we increase trust, changed framing or policy, or altered the cost structure of an intervention, would behavior change? Third level then is counterfactuals. This is where stronger causal and mechanism claims often live. Here we ask not only what happens if we intervene, but why did the outcome occur? And what would have happened different had X been absent? This is especially demanding in behavioral science because mechanisms often involve constraints such as beliefs, identities, motivations, or perceived constraints, many of which are indirectly measured and not directly observable. And so the important point is that behavioral science is often presumed to jump straight into layer 2 or layer 3. We are asked not only whether trust predicts compliance, but whether trust caused compliance, or whether a specific psychological mechanism explains why compliance occurred. But much of our observational evidence only supports layer 1. That's not a failure. It is only a failure if we overstate, what the evidence can justify. Correlational research is useful, insightful. It can point us to more causal claims. And so scientific rigor means matching the strength of the claim to the rung of the ladder that the evidence supports. And that leads directly to the next kind of issue, which validity. What justifies moving from data to a model? So now, how does this connect to the theoretical tools that behavioral scientists actually use? So frameworks like the COMBI try to organize constructs systematically so that so when you model, you don't accidentally omit capability, opportunity, or motivation. The choice of the framework is itself a modeling decision because it determines which constructs enter the data generating process. Later talks will probably show you or speak to how this is formalized. But returning to the kind of the notion of validity is that it's not an afterthought, right? It is the bridge between evidence and claim. Construct validity asks what are we representing, whether we are representing the intended construct. Internal validity asks whether the design supports the causal structure. External validity asks where, when, and to whom the claim travels. Statistical conclusion validity asks whether the estimate is reliable and precise enough for the claim being made. For an interdisciplinary modeling audience, the key point is that validity is not guaranteed by formal sophistication. A mathematically elegant model can still rest on weak construct definition, poor measurement, confounded design, or unjustified generalization. So the model is only the last link in the longer inferential argument. If the earlier links are weak, then the final estimates cannot rescue the claim. Take a simple example. Suppose we want to model whether someone's funds renewable energy windfall tax on fossil fuel companies. This is we tax their excess profits. We're going to use that to fund public, solar farms, wind farms, etc. Now, at one level, we might observe a behavioral outcome. Now, would this person vote for a politician who proposes the policy? At another level, we might ask about policy support. Do they approve of the policy? At another level, we might measure perceived fairness. Do they think that the policy distributes costs fairly? At another level again, we might measure ideology, trust in government, climate concern, economic insecurity, media diet, etc. Now, suppose that the model finds that perceived fairness predicts policy support. Now, what exactly have we learned here? We have not directly observed fairness as a substance in the world. We have measured responses to items that we interpret as indicators of perceived fairness. We have then modeled the relationship between those indicators and another measured outcome. Now, that may be useful. It may even be highly informative, but it is only as strong as the theory, the measurement strategy, the research design, and the causal assumptions that connect the observed data to the substantive claim. This is why inferential claims depend on the design and measurement. And if the study is cross-sectional, we should be cautious about causation. If the study is experimental, we still need to know whether the manipulation changed the intended construct. If fairness is measured generally, but outcomes are policy specific, then the claim must reflect that limitation. This also shows why construct precision matters. Fairness is not a unitary abstraction. There's distributional fairness, procedural fairness, personal fairness, recognition, reciprocity, and collective burden. All of these may behave identically, but have sort of different latent structures. Hence, a claim such as fairness predicts support is useful but incomplete. The more precise question is which kind of fairness, measured how, for which policy, in which context, and supports what kind of claim. Sorry about that. I should put that sooner. And so this leads to kind of a recurring danger in behavioral model, which broadly referred to as proxy verification. Proxy verification occurs when a measured indicator starts being treated as if it were the construct itself. When we say that we measured identity, for example, when often we measured responses to questions that we interpret as indicators of one aspect of identity. Or we say attitudes cause behavior, when the attitude then may reflect post hoc rationalization, prior behavior, ideology, or contextual exposure. Variables do not speak for themselves, right? They are made meaningful by theory, and that brings us to some common mistakes. The first mistake is treating measured variables as constructs. Right? A scale is not the same thing as kind of ideology, right, or identity, or motivation. Second mistake is treating a model fit as theoretical validity. A model can fit very well for the wrong reasons. Mistake 3 is confusing prediction with causal explanation. A predictive variable is not necessarily a cause. Mistake 4 is ignoring measurement error. Measurement error can attenuate relationships, inflate uncertainty, bias mediation models, and distort causal claims. The mistake is individualizing structural constraints. Non-adoption may not reflect unwillingness. It may reflect cost, access, infrastructure, time, safety, or institutional exclusion. Mistake 6 is assuming that constructs travel unchanged across contexts. A construct such as identity or autonomy may not mean precisely the same thing across groups, cultures, or institutional settings. These mistakes follow directly from the inferential cycle. They happen when we collapse distinctions that need to remain separate, such as phenomenon, construct, construct and measure, measure and variable, model and theory, estimate and claim. Accordingly, a beautifully estimated coefficient can still answer the wrong question. And so this is where I think mathematicians can contribute, and more than just sort of technical estimation. I think the most valuable contribution is formal clarity. What is the estimate? Right? What is observed? What is latent? What is assumed? What is identifiable? What is uncertain? How sensitive are the conclusions to alternative specifications? Behavioral science is full of mathematically interesting problems. Partially observed systems, multi-level dependence, dynamic preference, norm change, measurement error, feedback, reflexivity, heterogeneity, causal identification under imperfect designs. It also needs better ways to link theory to measurement and data generating processes. And the challenge is not just to build more complex models, but rather to build models that are tractable, transparent, and faithful to the behavioral object of interest. Mathematics contributes most when it clarifies assumptions, when it quantifies uncertainty, and makes the structure of the data generating process explicit. And so let me expand on what some of these challenges might look like technically. So first, identifying latent constructs in noisy self-reports is fundamentally a measurement invariance problem. We need formal tests and sensitivity analysis for whether a questionnaire measures the same construct across cultural groups, policy contexts, and time periods. It's not psychometric like nicety. It changes whether the coefficient you estimate is a true effect or a measurement effect. Second is modeling dynamic norm change. This requires dynamical systems thinking. Norms are endogenous, right? As behavior changes, norms change, which feeds back into behavior. So static regression models can't capture that. We need formal kind of tools to handle feedback, path dependence, and tipping points. Third, be quantifying construct drift. Right? This is essentially a problem of model misspecification over time. If the meaning of trust, for example, changes with a political scandal, then our latent variable is not stationary. So how do we formally detect and correct for that? So when I say contribute, I don't mean like running our regressions for us. I mean co-developing the formal machinery to make our inferential architecture robust to these uniquely behavioral challenges. And just to expand on this a bit more. Additionally, like how can we make reliable inferences when, for example, observed responses are produced jointly by the phenomenon of interest, the measurement instrument, and the respondent's decision about whether and how to answer. Back to again the reliance on questionnaires, surveys. Right, a big issue, or at least an ongoing kind of debate, is should surveys offer a neutral midpoint? Removing it may force respondents to reveal directional leanings, but it may also manufacture opinions that don't exist. Including it may represent a genuine neutrality, but also produce a route for satisficing. The methodological question is thus which latent response processes are identifiable from each design. So an additional, and I think very valuable contribution would be the development of more principled protocols for inference under response uncertainty and imperfect response skills. More specifically, we would very much kind of value your help in developing robustness standards, right, which are analogous to, I think, diagnostic protocols. And so, using these or developing these for determining when results depend excessively on arbitrary coding, on imputation, or exclusion criteria. And so I would therefore propose kind of a practical checklist for behavioral modeling. First, what is the behavioral target? Right? Is it an action? Is it a choice? Is it a self-report? Is it a habit, an interaction, social practice, construct? Right? Second, what level of explanation is being modeled? Is it the individual cognition? Is it interpersonal influence, individual constraint, cultural meaning, or some interaction between these? Third, what is the measurement process? Right? Are we using self-report, observation, digital traces, administrative records, experimental task, interviews, or coded text? Fourth, what kind of inferential claim is warranted? Is it description, prediction, explanation, causation, mechanism identification, or policy evaluation? Fifth, what rival explanations remain? It's confounding, reverse causality, measurement artifact, selection bias, omitted context. And six, what evidence would make us change our mind? And I think that last one is very critical here. Right? A model that accommodates every possible outcome is not explaining enough. And so theories need risky implications, anomalies, and opportunities for revision. And so I want to close sort of by returning to the title question. Right? What are we modeling when we model human behavior? Sometimes we are modeling observable actions. Sometimes it's reported attitudes. Sometimes it's choices under constraints. Sometimes it's interactions. Sometimes it's latent constructs. Sometimes it's individual responses. Sometimes it's cultural meanings. Often it's the relations among all or many of these. So the core task is not to reduce behavior to a single variable or to simply collect more data, nor to reject modeling because humans are complex. Right? We know they're complex. The point is to make sense of that complexity. Right? And so the corollary task is thus to specify carefully what the model represents, what it leaves out, what assumptions connect data to theory, and what kind of inference the evidence can support. So my central claim is this: robust behavioral science depends on keeping the layers distinct: phenomenon, theory, construct, measure, model, estimate, and claim. When we preserve these distinctions, behavioral science becomes not less but more rigorous. Whether it becomes clear about what is observed, what is inferred, what is assumed, and what remains uncertain. And I think that this is where kind of interdisciplinary collaboration with mathematicians, statisticians, computer scientists, computational scientists can be especially powerful, and not by treating behavior as just another parameter, but by helping us build models that are conceptually explicit, empirically disciplined, causally cautious, and theoretically meaningful. That was a lot faster than I thought it would be. Sorry.